We now talk about cup product. Everything here you can find in Hatcher. So you first start with the chain complex. So this is the chain complex in homology, and you have these boundary maps right here. So from here you construct cochain complexes. What you simply do is you put rings like this. So this is ID map here. And we had put integers here before, and then you compose partial with this map, and composing these two maps, since this is a equal here, you get these maps D. So we rewrite this portion as C4, and then you have a map coming in, the arrows have reversed. Then you have C3 is these maps, you have C2, you have C1, C0, and this is how it goes on. And you have these co-boundary maps now D here. So what is the maps here? What are the maps here? So the maps here are nothing but functions acting on say a complex. So let us rewrite this. So you have functions which act on this thing: v0, v1, v2, v3, v4. There's some simplex or delta complex like this, and this cochain complex means functions which are acting on this. So say there is a function f which acts on all of this. So this is the function f here. Now consider two functions here in C2. Say you have function f1 and you have another function f2. Now these functions could also act on this. Say f1 acts on first three vertices 0, 1, 2. So it is on C2, acts on three vertices C2, 0, 1, 2. So this is f1 acting on it. And then there is an f2 which again acts on three vertices 2, 3, 4, or you can renumber them as v0, v1, v2 for here. So this is f2. So both f1 and f2 lie in this complex here, and you can see if you combine them both, so combined both f1 and f2, you combine them both, they act on C4. So basically what we are trying to do is we want to combine this f1 and f2 to land it in C4. So this combination we will write as a cup. So this f1 cup f2 now lies in this complex. So f1 cup f2 can act on these 5 vertices or on this C4. Similarly, you could do with C1 and C3. So say there is a function g1. So g1 lies here. So g1 lies in this C superscript 1. That is, g1 acts on 0, 1. So this is where g1 acts on. And g2, this lies in C3. So here is g2. So C3 means it acts on 4 vertices 0, 1, 2, 3. So 4 vertices 0, 1, 2, 3, or you can say v1, v2, v3, v4. So this is say g2. So g2 lies right here. So acts on 4 vertices here. So again you combine g1 and g2, they are basically acting on these 5 vertices or lie in C4. So you have g1 cup g2, this also lies in C4. Similarly, you could have something here in C0. Say you have H. So say H is belonging to this. So now you can have H just acting right here, and this rest of this is some map in C4. So rest of it is say some map, call it say phi. So phi is here and then H is here, and you combine them both, it still lies in C4. So You combine them both, it still lies in C4. So this acts something like an identity. So this should remind you of polynomials. So you have x multiplied with x cube, you land in x4. And that's what happened here. You combined G2 and G1 and you landed up in C4. Similarly, you have x square, you land up in x4. So x square, you land up in x4. So there is some kind of a polynomial structure going on in here. So you can see this structure comes in because of the maps acting on the underlying chain complexes. Now, since we are in cohomology, we are going to talk about cohomology groups. In fact, this entire conversation is arising because we want all these maps, these cup products or combinations, to act on cohomology groups. Because we are working in algebraic topology, from space we want to go to category of groups. So we want this to act on cohomology groups. So these cohomology groups, they consist of two things. They consist of cocycles and coboundaries. And we obviously want these combinations or cup products to respect these cocycles and coboundaries. So there should be some condition on these cup products so that these cocycles and coboundaries are respected. So for example, say you have two cocycles. So say two cocycles are f1, you apply d to it, it is 0. So f1 is a cocycle, and say f2 is a cocycle. So d of f2 is 0. And we will remain as before. F1 and f2 lie here in C superscript 2. So you land up, if you take f1 cup f2, you land up in C4. But if you take d of it, so we want d of f1 cup f2 to be 0. So something like it will become d square, and you know this d square is 0. So if you have two cocycles, you take their cup product, you will land in C4. But if you take d of it, then it should give you 0, because d of both of them is 0. So that way you can pass on from here to cohomology groups. Second condition we want is, so the second condition is simply this. You have say this is df and this one is dg, that is this var phi and phi, they are both co-boundaries. So they are co-boundaries because they are d of some maps. Now if you take their cup product, you will land somewhere, but then if you take d of it, it should give you 0, because cup product is something like a multiplication. Yeah, x times x square should land you in x cube. So if you take this will give you something like d square, you take d of it, it should give you 0. Yeah, because anyway, if you have cup product of these two, then this should end up as 0. And the third thing is, say you have a co-boundary and a cocycle. So say you have df is 0, that is f is a cocycle, and say you have, say, a var phi is a co-boundary. So when you take the cup product of this, the cup product of f and var phi, you should get a co-boundary. Yeah, because only one of them, when you apply d to it, is 0. So that is, you want we want this. So you take the cup product, it should be co-boundary of something. So that is pretty much it. This is what we require so as to pass to cohomology groups. Again, cohomology groups just consist of cocycles and co-boundaries, so we have to consider applying cocycles and co-boundaries on these cup products. In fact, all our prayers are answered. So let us see this. So we will rewrite this again. So say this var phi belongs to Ck and psi belongs to Cl, then you take the cup product, it belongs to Ck plus L. Just like you took two elements in C2, you took their cup product, you ran it in C4. So more formally, this is it. This var phi acts on first k vertices, and this psi acts on starting from k to k plus L. So this is k plus L. So this belongs to Ck, this belongs to Cl, then the cup products belongs to Ck plus L. And this sigma is nothing but the embedding. So this is how the nice delta complex looks like. What does sigma do? It embeds into some ambient space X, and then this delta complex might look like this. So doesn't do anything much to it. So this is precisely what we have done here. Now the lemma, which we will prove later on, this tells us that d of this cup product is d of var phi cup with psi plus minus 1 to the power of k, this var phi cup with d of psi, and where this var phi lies in Ck and this phi lies in Cl. Now this result answers all our prayers, all these three conditions. So let us see this. If both d of var phi and d of psi are 0, that is both these are co-cycles, then you can see this is 0 and this is 0. So you sum it up, it is 0. So the cup product itself is a co-cycle. So this cup product, you take d of it, it becomes 0. So d of cup product means that it is a co-cycle. So this is our first condition. Second is cup product of a co-boundary and a co-cycle is a co-boundary. So first, if d of phi is 0, that is this var phi is a co-cycle. So if you take d of a co-cycle, you get 0. So if this is 0, then you take the cup product, d of this cup product, this term will become 0, and what is left is this term. So you have phi cup of d of psi, this, and then this minus 1 you take on this side, you get plus minus d of this. So the cup product is a co-boundary. It is a co-boundary because you have a d here. So again, this phi was a co-cycle because d of phi is 0, and then you are taking cup product with the co-boundary. Obviously d of something is a co-boundary, and so cup product of a co-cycle, this is a co-cycle, and a co-boundary is again a co-boundary. On the other hand, you could have taken this term 0. We could have taken d phi of this term as 0. That is, this psi is a co-cycle. In that case, we have that this term would have been 0. This entire term would have been 0, and you are just left with this term. So d phi, this cup with this is equal to d of this. So again, you get a co-boundary. And similarly, you can check the third condition. Yeah, in the third condition, you simply so this is the third condition we have checked here. So this was the third condition we have checked here, and you can check the second condition. Second condition is simply because you will take the cup product here, you will get d square here and then d square here. So in this condition here, you get d square here and d square here. That will give you 0. And therefore, since you are preserving co-boundaries and co-cycles, so this induces cup product cohomology, and that is pretty much it. This is from here, this cup product passes on to cohomology groups. Now the beauty of this is that we will be able to put this into action, because we know the cohomology groups of a torus, RP2 and different structures, and we want to calculate cup product on them. So since you know cohomology groups, you can play with these cohomology groups and find some structure. So the only thing now remaining is the proof of this lemma. So let us focus on this term first for the proof. So first we focus on this term right here. You copy it down, apply it on sigma. So you apply this first d phi on k plus 1. Notice that now we are going to act, this sigma is acting on k plus l plus 1. Yeah, here in the definition we were acting on k plus l. The sigma was k plus l, so they had k plus l vertices in sigma. Now it is k plus l plus 1, and first k plus 1 vertices are here. So here we had k vertices, here we are taking k plus 1 vertices. So that is the only change. I'm just following Hatcher. Even you could have just put k here, but I think it helps in thinking later on in the proof. So this plus 1 doesn't do much harm. Then you multiply it starting from vk plus 1. You put vk plus 1 all the way to k plus l plus 1. We'll just copy down this definition right here. Now this we had defined this d as you have var phi, and then you apply this partial to it or del to it, and this del is nothing but this comes from homology. So this del, when acts on this singular simplex, you get something like this, you know, minus 1 to the power of I, and then you have this vertex missing. So this is exactly what it is in homology, and we copy down this definition of applying partial to this sigma. This partial is applied to this entire sigma, or you can say from v0 to vk plus 1, and that is how you get the summation sign and minus 1 to the power of I. This second term you don't even touch, you just copy it like this. Now we focus on this part. Now for this part you have this minus 1 to the power of k, you keep as such, and this phi acts on first k vertices, and then this d phi acts on k to k plus l plus 1. Yeah, so very important thing to notice here is this var phi is part of ck. Just like here, var phi is part of ck and the psi is part of cl. So automatically d of var phi is part of ck plus 1, because d will push it 1 degree higher. So that is why you have d phi acting on k plus 1, and this var phi, this is part of cl, so you are going from k plus 1 to all the way to k plus 1 plus l, or k plus l plus 1. So you have var phi acting here, part of ck, and then there's d phi, this will go 1 forward, so acts on one more vertex. So instead of vk plus 1 you have another vertex here, which is vk. You start from vk to vk plus l plus 1, so one more vertex. So again, you know, this d of this thing is nothing but, so you have to apply this del to this entire piece. So when you apply del to this entire piece, the problem is that you will have to start from vk. So you have to reindex this. So if I apply del to this vk, so if I apply del to this entire thing, vk plus 1, vk plus 2, all the way to vk plus l plus 1, then you always have this minus 1 term coming in. So when you omit the first vertex, you will put 0. When you omit the second vertex, you will put 1. You omit the third vertex, so when you omit vk plus 1, you will put 1 here. When you omit vk, you have 0. Now that is a problem, you know, you have k here, you have 0 here, you have k plus 1 here, you have 1 here, and so on. So we want to make sure that this thing, this 0 should be k, this 1 should be k plus 1. Then you, if you omit vk plus 2, if I simply apply this partial to it, this will be just 2. Now this, the beauty of multiplying by this is that you multiply throughout by minus 1 to the power of k. This k comes in here. Partial would just have given you 0, 1 and 2, but multiplication here will give you k, k plus 1 and k plus 2. So you have something like this: I is equal to k plus l plus 1 minus 1 to the power of I. Now we just add this term and this term. If you add these two terms, this k plus 1 term here will cancel out with the kth term here. So you can write it down, the k plus 1 term and k term, they will have opposite sign because you have minus 1 to the power of k plus 1 here, and you have 1 to the minus 1 to the power of k here. Everything else will be the same, so those two terms cancel out. So you add these two, what you will get is, after writing it down, it will just be simply cup of this var phi cup with psi, and you have a partial of this sigma. So that is pretty much it. If you add it up and you write it down, that's what, or you can expand this and see it for yourself. And we have seen the usefulness of this formula. So this proves the result. So you will get this, and this is nothing but this result, d of. So again, everything here is in section 3.2 of Hatcher.